So, the actual storage format that we use in order to store data in memory actually starts to become important, and let us take a couple of examples to try and understand why that is the case, right. So, one thing to keep in mind of course is inside a computer memory you have only binary zeros and ones, right. Typically in reality this would be either some positive voltage or 0, which is ground voltage, right, some reference, and how we maintain those two different voltages is what decides whether a particular transistor or some physical circuit element is actually storing a 0 or a 1, right. Now binary is what is actually there, but on the other hand it is very hard for humans to understand, right. We would prefer to work with decimal of course, because that is what we grow up with, that is the number system that we are typically most comfortable with, because we have 10 fingers, so it is easier to compute or count in terms of multiples of 10. Of course it is possible to also count in other multiples, but you would need to practice that right from a very young age to become really comfortable with it. On the other hand, there is also hexadecimal, which at least is more readable than binary in the sense that it is more compact, right, and therefore it is possible for humans to at least think in terms of hexadecimal numbers, but at the same time is also very easy to convert between binary and hexa, right. As an example, if I take the decimal number 1234, right, the binary equivalent of that I am treating it as a 16-bit number, right, so that I do not have any issues with 2's complement, positive, negative and so on. I very clearly have leading zeros out here, right, several leading zeros in fact, and I am going to say that the binary equivalent of that is this value out here. I am not even going to try reading it, right. It has a lot of zeros, a lot of ones, but if you work out the math, it will actually compute to this number 1234, 1234. Okay. Now the interesting thing is conversion between the binary and the hexadecimal is actually very easy. All I do is I basically take it in groups of 4 at a time and convert it to the corresponding hex digit. Why is that? Because there are 16 different hex digits from 0 up to f, which take all the possible 4-bit values from 0000 up to 1111, right, and it is literally a 1-to-1 mapping. 4 zeros corresponds to the hex digit 0, 0100 corresponds to the hex digit 4, 1101 corresponds to D, it is actually the number 13, right, which 1101 is 13, D is 13, and therefore 1101 will always map to the hex D, and 0010 is the hex value 2. So this binary value, whatever it was, which I am not going to try to read, can be very compactly and easily represented as 04D2 in hex, quite easy to read, pronounce, etc. Right. Now of course if we think in terms of how do I store this value, what you can see is I need, if I am working at a byte granularity, I need at least 2 bytes in order to store this decimal value. If I am looking at the bit granularity, I could argue that maybe I could have done it with 11 bits if I was working only with unsigned numbers, or with 12 bits where there is no confusion about whether it is 2's complement, signed, unsigned and so on. It is very clear this is a positive number. So 12 bits would be sufficient for storing 1234, but my granularity is at the byte level, and therefore what I am saying is I need 2 bytes, right. Now comes the tricky part, because the order in which these 2 bytes are stored in memory actually matters. It is something that we would normally never think about, because all that I am thinking about is I need 2 bytes, sure. Now the question becomes, okay, let us say that I want to take this 2 byte value and store it at memory location 0. Should the 04 go into location 0 and D2 go into location 1, or 04 go into location 1 and D2 go into location 0? That is what I mean by the order of bytes. And what happens over there is there are a couple of different ways of visualizing memory, right. One of them, the way that I like to think about it is, it is sort of like having a long ribbon or a tape that you stretch out from left to right, okay. And normally, at least in the kind of languages that we are used to, right, English as well as most Indian languages, we tend to write from left to right, and therefore we would think of this tape automatically as starting from memory location 0 and going towards the right 1, 2, 3 and so on up to some n minus 1, where n is the number of locations. Further, I am assuming that each and every one of these locations is capable of storing 1 byte. Okay. With all of that in mind, what would I do? Probably if I told you to store the value 04D2, you would go and say, okay, the first byte 04, put it in location 0, second byte D2, put it in location 1. Okay. This looks very logical, straightforward and the natural thing to do. And of course, just like with any other natural things, it turns out there is more than one natural way to do it, which is the other way of looking at it is, what about thinking of memory as this big box, right? And over here what we have is, we actually think in terms of the low memory, which is these low values out here, and high memory, which is high values out here. And it turns out that at least in the way that a lot of computers were developed to start with, people actually thought explicitly in terms of low memory and high memory, and actually had this notion of memory as being something which grows upwards, right? Why do we do that? Because we want more storage, we can pile another block of memory on top and so on. Okay. The intuition behind it is beyond a point, you can't really explain it. You could always argue, why didn't people just stick with the tape view? Well, what they asked is, why not just stick with this view instead, right? Both have their pluses, both have their minuses. The point is, this is a different way of looking at it. But now the tricky part over here is, when I am given a memory block like this and I am asked to write something into it, when you are given a sheet of paper and asked to write something, mostly what you would do is start writing at the top and make your way down. And that is precisely what people did over there. They basically said that the 04 now belongs in location 1 and the D2 over here belongs in location 0, right. So you can sort of see that I have the 04, when I go from left to right, that is the tape-like view, 04 goes into location 0, but in the high mem low mem version 04 goes into location 1. In the other viewpoint, which is, and the second byte, the D2 goes into location 1 in the tape and goes into location 0 in the high mem low mem version. Which one is correct? Fundamentally there is no clear cut answer to this, both could be correct, right. So this in fact led to a lot of discussion, and why it is important is because which option we choose determines how we interpret what we see in memory, right. If I just ask for what is stored in location number 1 and I do not know whether the person who built this computer was thinking of a left to right tape or a top to bottom stack of memory, right. I do not know whether the data stored in location 0 is the next byte or the previous byte, right. It would depend on which way I am looking at it, and this is essentially referred to as something called Endianness, right. Which end of the 2 byte value should be stored at the lower byte address, okay. Now the origin of this term Endianness actually comes from the sort of children's story or a political satire, depending on whichever way you want to look at it, called Gulliver's Travels, right. And there is this notion over there about how there were people who argued about which side of the egg, a boiled egg, should be actually cracked open first, right, whether you should take the wider part, that was the big end, or the narrow part, which is the narrow end or the little end. So obviously people who had worked on computers for long enough found that this entire argument over here had descended into the point where it became a bit of a joke, right, and as sort of a tongue-in-cheek way of putting it, they said, hey, let's call it either big endian or little endian so that we can continue our arguments forever. So the point is that a big endian storage takes the approach that we are going from left to right. Why it's called big endian is that the most significant byte, as you can see over here, this 04, right, which is the more significant byte of the number 04D2, gets stored at the lower memory location, at the lowest address, right, or you could think of it as at the leftmost address, depending on which way you want to look at it, right. The little endian sort of follows the top to bottom approach and says the most significant byte should be at the highest address, right. Now, as you can imagine, both sides have a case to make, right. It is not entirely clear that one is right or the other is right, both, I mean you could argue either way about it, but which one you choose finally does matter, because otherwise they can't talk to each other, okay. So, in particular, let us take this one example which is not just 2 bytes but 4 bytes, an integer, right. So, how would you store this integer value, which I am writing as its hexadecimal notation, right, 1, 2, 3, 4, 5, 6, 7, 8. This 0x in front indicates that it is a hex value that I am talking about, but why I am using hex is because it is very easy to identify the bytes. 1, 2 is the first byte, the value of the first byte, 3, 4 is the value of the second byte, 5, 6 is the value of the third byte, 7, 8 is the value of the fourth byte. 1, 2 is the most significant byte, 7, 8 is the least significant byte, okay. And with that in mind, the big endian notation would say that 0x12, the most significant byte, would go into memory location 0, 3, 4 would go into 1, 5, 6 would go into 2 and 7, 8 would go into 3, while the little endian approach would say the least significant byte goes into location 0, the most significant byte goes into the highest address 3. As you can imagine over here, right, what is happening is that the memory addresses are increasing this way or increasing upwards for the case of little endian, right. And obviously, if I just took exactly the same data and switched the processor from something that was so far interpreting big endian to something else that interprets little endian, I am going to read the data all wrong, okay. So, this actually does matter. So, couldn't people just have come to a convention or a common approach just like everything else? No, it turns out that there were enough people building processors independently of each other, each with their own strong opinions, that neither side actually completely won out, although these days to a large extent little endian is probably the more popular way of looking at it, or more popular simply in the sense of the number of computers that accept little endian, right. There were older machines, notably the Sun Spark and a lot of Unix workstations which followed big endian notation, right. ARM and the RISC-V processor are things that sort of have good support for doing things both ways, right. They can sort of switch between the different notations without too much difficulty. Now, even though the x86 follows little endian, x86 is the Intel AMD type of architectures, and therefore in raw numbers the maximum number of CPUs are probably over here. Possibly, I mean you could argue about ARM at this point, but at least desktop workstations and servers, x86 is still what rules. So, little endian is clearly very popular, but one place where it actually makes more sense to think in terms of big endian is what is called network byte order, right, where we are actually transmitting data across a wire, let us say, right. And in that case, why it becomes important is the big endian is a more natural way of thinking about how the data, the bits actually come onto the wire at any given different point in time, okay. So, network byte order, in other words, a lot of network applications tend to use big endian notation, right, and what that means is little endian systems must convert from network byte order into their internal order and vice versa. But it turns out that the hardware support for this is fairly easy, and so nowadays this is not really so much of a point of contention or point of argument. People pretty much accept both, okay. So, let us look at a couple of examples of actual code where we can sort of visualize what happens with the word sizes, right, and word sizes or how pointers are used. So, over here once again I have got a function that only pretty much uses this internal function of C, right, called sizeof, right. Sizeof is a somewhat peculiar function. What actually happens is it is pretty much computed at compile time, right, but it can be used in order to find out what the various different parameters that you are trying to work with are, right. So, what you can see over here is in this function I have defined p as a void star pointer. What is void star? It basically says it's a pointer to a memory location, but I don't know what's at that memory location, right? Why is that important? Because if I knew that it was a char, then I would know that my pointer is pointing to something that's 1 byte wide. If I knew it was int, I would know that it's pointing to something that's 4 bytes wide. So if I try dereferencing it as star p, I should actually go in there and try and look for 4 bytes if it's an integer, right? But when I declare it as void star, basically the compiler says I don't know how big the data is supposed to be, okay? Now what happens when I run this? It actually tells me that in this particular case, because this is a Linux system, right, the size of int is 4, the size of long is 8, and the size of a pointer in this case is also 8. This, remember, is the number of bytes. Therefore, the number of bits is 8 into 8, that is 64. For int it is 4 into 8, 32, and for long it's 8 into 8, 64. Okay. So this is one way. If you are unsure, right, you can just write a small program out there where the compiler itself will tell you what it assumes for the different sizes of data types, right. Now one other thing that you can notice over here is that if I actually look for the size of star p in this case, right, it actually prints out 1 over here, right. And in this case it turns out that the compiler is actually taking this approach that I can actually find out what is at star p. I will just basically take it as the default, right, which is that it's just pointing to 1 byte, and therefore give you that p is a void pointer, it points to a certain location in memory. Right now p actually does not have a value, but if it did and it pointed to a location in memory, it would be pointing to something that was 1 byte in size, okay. The thing is, this is not actually something that's guaranteed by the compiler, by the language, right. It's possible that the compiler might instead decide to give you an error and say that, look, I can't run this program for you, okay. So keep in mind that the word sizes are things that are dependent on the actual application that you have, right, and if you are in doubt, it's probably good to actually check on what the actual data types are that you are working with. On the other hand, if you do want to precisely get exactly what the size of a given variable is supposed to be in C, you could bring in this header file stdint.h, right, and with that you could then ask for a uint32t, which is an unsigned integer of size 32 bits. So we should see that the size of uint32 is 4, that is 4 bytes. Or you could ask for an int64t, which is a signed integer of size 64 bits or 8 bytes, right. And as you can see, it dutifully prints out those values, right. uint32 is 4 bytes in size, uint64 is 8 bytes in size. If you want precise control over the data types that you are using, it's always preferable to do something like this. Now this function over here actually gives a brief demo of the Endianness problem, right. What we are trying to do over here is I declare a as an integer and give it the value 0x12345678, right. So I know, because it's in hexadecimal, that the most significant byte has the value 0x12 in hex, which is 18 in decimal, right. The second most significant byte has the value 0x34 in hexadecimal, then 56 in hexadecimal, and finally 78 in hexadecimal. But now what I am doing is I declare a pointer, right, a pointer to a character, and then I say I am going to take the address of a, which is ampersand a, but treat it as a character to a pointer. This is called typecasting. We will look at it a little bit again later, but what it says is I can take the address of a and now I can interpret it as a character pointer and therefore assign it to C. From this point onwards, C is a pointer to a character which has the same address as the address of A, right. And now I can basically go in there and look at the different values that are present, right. So what we can see over here is that it actually prints out that when we run this for loop out here, it prints the 4 characters that are accessed at C of I. Now the C of I is again a notation that we will see more of when we go into discussion of arrays, For the time being, what you can think of is that C of 0 corresponds to whatever is at location that is given by that address, C of 1 is the next address, C of 2 is the next address, and so on, right. And what we can see over here is that C of 0, that is the address location 0, has the least significant byte, whereas C of 3 has the most significant byte. This is what we expect, because after all this program is running on Replit of course, but on an x86 class processor, right. We can also get the addresses of the individual locations, right. How would we do that? We could, for example, ask it explicitly for the address and say so what I have done in this case is to actually take the address of C of I, typecast it as unsigned long simply so that I can print it out over here, and then let us go take a look at it. And what it tells me is, I see this huge big number out here, right, which it turns out is actually the decimal representation of some address in memory, which may or may not be a physical address, we will get to that later, where the least significant byte is actually stored, right, and that is something 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 92. The next byte is stored at something something 93, then 94, and then finally 95. Okay. So, even though I thought of it as just 0, 1, 2 and 3, it turns out that the actual addresses that are there are something more complicated, right. The point is, it does not matter, we actually have something which has gone and stored things with the most significant byte at the highest address, least significant byte at the lowest address, and I can retrieve it in any way that I want. What this is actually telling us is that the int A that I had out here was actually being stored at these 4 memory locations. And interestingly enough, if I then go and ask for the location of int A, as you can see, the address that I got for A and the address that I got for char of 0 are the same. That was exactly what I did out here, right. I took the address of A, converted to a character pointer, and then assigned it to C, right. So, even though all of this what is written out here might end up looking confusing, what am I doing out here? The way to break it down is always to think in terms of, let me think in terms of the memory, right. A is a name of a variable. What that means is some place has been allocated for it in the memory of the system, and the address of that turns out to be this number out here. Now, if I want C to be a pointer to a character, right, and to have the same address as A, I first take the address of A, tell the compiler to now treat it as a pointer to a character and assign that into C. Easy enough, right. So, C of 0 has exactly the same value as the address of A, and both point to exactly the same location. And because x86 processors are little endian, it turns out that C of 1, 2 and 3, the next few addresses, contain the remaining bytes corresponding to whatever was stored in A, right. This is worth actually thinking about and playing around with this code over here to make sure that you understand exactly what happens. And the way to think about it is always in terms of a pointer is just something that is pointing to some location in memory. What is at that location? It is a set of bits. Do I want to interpret those bits as a byte, as a character, as an integer, as a floating point number? That is up to me. Okay. What matters is there are bits present over there. And by having these different kinds of pointers and by accessing the same memory in different ways, I can actually interpret the data in different ways.